You can, however, do linear systems of equations with three variables. And so if we have an equation with, like this, with x and y and z, if you need three variables, you're going to need three facts to be able to solve for those. So we're going to have three equations in three variables in this case. And so essentially what you do is a step-by-step process to either substitute one variable out, solve for x in one of the equations and plug it into the other x's in the other equations to get rid of x's. That you can do a substitution that way, or you can eliminate one variable. But it's going to take more steps than a 2x2, and I'm going to show you a couple examples how to do that here. Again, like I said, it's easiest to, when you're doing these notes, to remember what steps you've done along the way. So if you go back and look at your notes, you'll remember what you did. I like to label my rows. Equation 1, equation 2, somehow that looks weird. I do it with rows. And you also might have eventually solved this by matrices at some point. And so in that case, it's much easier to talk about rows of a matrix. And so R1, R2, R3 help me remember what I start with. And so I'm going to take, so in this case, again, I could choose whatever variables I want to eliminate to make my algebra easiest. I could eliminate the x's by, I could take R2 minus 4 times R1. And what would I get in that case? I would get 4x minus 4 times x, I get 0x, minus 5y plus 4 times 5y would be plus 15y. 4z minus 4 times 5z is going to be 4z minus 20z, which is minus 16z. And I'm going to have 19 minus 4 times negative 2, that's 19 plus 4 times 2, 19 plus 8, that's 27. So I could go and eliminate the x, and then I'd have to eliminate the x in row 3 as well. But I wanted to show you, I worked it out with eliminating y instead. So let me do that example. Let me say I'm going to look at this column and eliminate the y's, because they're all 5 times y. So I don't have to multiply any equation by 4 or by some other constant. I can just add row 1 and row 2. And when I add the 5y and the minus 5y, they go away. So I get 5x plus 9z is 17. And then I can consider row 1 and row 3. And if 5y and 5y, I have to subtract. Row 1 minus row 3. In this case, the x's also cancel out, which is just lucky. It saves one step. 6z minus 18. And so now we're going to rewrite reorganize your equations. Now I'm down to two equations with x and z in it. I've eliminated y. 2 variables, 2 unknowns. I can solve by what we've done before, either substitution or elimination. Just because I did elimination at the first step doesn't mean the second step I have to do elimination again. In this case, though, I get a little lucky. And there's no x in the second equation, so I don't have to worry about that. This just 6z equals 18, so z equals 3. Once I get z equals 3, I can plug that back into the previous equation, like here, and solve, and x equals minus 2. Once I get z equals 3 and x equals minus 2, I plug both of those back into the other equation, an equation that had y as well, and I can multiply those out and solve for y, and I get y equals 3 in this case. So when I'm all done with this equation, I get 3 variables. Each one, z is 3, x is minus 2, and y is 3. Another example of how this might come up, there's an example in the book that's from electrical engineering. And I don't know anything about electrical circuits, and you don't need to for this, but I'll explain a little bit. If we have a little diagram here where we have wires around here and there's a wire across the middle, there are 3 paths through this. And so there's path A through the middle, and there's path C across the bottom. And so on each of those, I could have a different voltage, a different amount of current going through there. And so I want to figure out how much of current is going through A, how much current is going through B, and how much current is going through C. And there are some rules called Kirchhoff's laws and Ohm's law, which we're not going to really worry about. But I have, at this point, there's A amount going in, and there's B going out on this way, and C going out on this way. So A has to equal B plus C. So A minus B minus C is 0. That's one fact. Then we've also got each of these little circuits in the middle. So this circuit around there from A to B and back, these squiggly things are the resistance. And so there's a rule that says B times 1, the resistance on that, plus the resistance on the A, which is 4 times A, has to equal the voltage. And so 4A plus B has to equal 9. Okay, so that's one fact. And we'll just take that for granted. I'm not going to ask you to know this. I've written it down. And then there's another one where you have the bottom circuit, where you might have B and C. And again, I've got 1B, and I've got, over here, I've got 3 resistance plus 2 more resistance, that's 5, and that has to equal a total of 4 volts. I'm not even pretending, I don't understand the physics and the electrical engineering of it, but we'll just go with it. We get an equation like that. How can you solve that? So we break it down to get this box of 3 equations with 3 variables, A, B, and C. So I'm going to do, take the first one, it's easy, A equals B plus C, and I can substitute that in, okay? Again, we got lucky, this third equation has no A in it, so we don't have to substitute into the second equation, but if there was an A term here, we'd substitute into that as well, and you could do that, and at that point, you'd only have B's and C's in your equations. You'd have 2 equations with B's and C's in them, so you're able to, you have to simplify them a little bit, but you're able to regroup them into a system of 2 equations with 2 variables. Then you can solve. And again, you can decide if you want to do elimination or substitution at that point. And so I chose to do substitution. I took one of those equations and solved for B. So I took this second equation and solved for B, and then plugged that in to the first equation. You notice if you plug it into the same equation you solve for, if I instead plug this into the top equation or the bottom equation again, everything would cancel out and I get 0 equals 0. So make sure you substitute into the other equation. And when you do that, you multiply everything out, move the C's to one side, solve for C, and in this case it comes out nicely, C equals 1 volt. And once you know one variable, there's something called back substituting. And so that means you take that C equals 1 and you plug it back into the previous equation that just had C and B. And then I can solve for B. In this case, it also equals 1. And then I can take C and B and plug those in to the original equation, A equals B plus C. And I can find that A equals 2 in this case. So around my circuit, I had 2 going across the top and 1 going across each of the other 2 when it splits into B and C. So that's an example of 3 variables and 3 equations, and you know now the process, either substitute or eliminate of 1 variable at a time to bring it down to 2 variables and 2 equations, and then repeat. It's a long, tedious process. In my cases, the algebra worked out pretty well. Some examples in the book, the algebra is going to be pretty ugly. Just be a little bit patient and try and keep yourself as organized as you can. Rewrite your systems of equations in blocks and kind of step by step by step. Organization is the best way to solve these problems. Good luck.